This is the third video on ions and ionic compounds, and this one will be on how to put ions together to make an ionic compound. There are three concepts that we deal with when doing this. The first is that opposites attract. Positive and negatives are attracted to each other. The second, the overall ionic compound has to have a net charge of 0. And the third is Coulomb's law. Since we are dealing with electrical things, Coulomb's law will come into play here. So let's start with opposites attract. All ionic compounds are dichotomous. They must have a cation or cations. That is either going to be a metal or ammonium. And it's going to have an anion or anions, which will either be a nonmetal or one of the other polyatomic ions. The overall ionic charge of a compound is 0. We talk about the total cationic charge, which is the number of cations times the ionic charge of the cation. Then there's the anionic charge, which is the number of anions times the ionic charge of said anion. And when you add those two numbers up, you should get a value of 0. Now, to make compounds, there are many different ways of tackling this. We're going to deal with a crisscross method, but if you come see me, if you need another method, I'll be happy to show you others. And there are 4 steps to the crisscross method. In the first one, you write out the ions. In the second, you get rid of the plus or the minus sign. You're then going to crisscross the numbers. You'll see when we do the example. And then you make sure that the subscripts that you crisscrossed are in the lowest whole number ratio, and we're going to abbreviate lowest whole number ratio as LWNR. Let's start with an example. What is the ionic compound made from gallium and sulfur? First step, write out the ions. Gallium is 3 plus and sulfur is 2 minus, both of which we get from the periodic table. Now we're going to get rid of the plus or the minus sign on the charges, so it looks like this. Now we're going to crisscross the number. The 3 comes down to here, and the 2 comes down to here. So it looks like this, and we put the things together, and it looks like that. And now we make sure that the subscripts are in the lowest whole number ratio, and 2 and 3 are the lowest whole number ratio. So we would say that this is the formula. Now the double check. Gallium, of which we have 2, has a charge of 3 plus, so we say the total cationic charge is 6 plus. Sulfide, of which there is 3, each sulfide has a charge of 2 minus, so the total anionic charge is 6 minus. 6 plus 6 minus equals 0. This is a valid formula. How about iron 2 and carbonate? We're going to do the same thing. Write out the ions. Iron 2 is Fe2 plus, and carbonate, one of the polyatomics you should have memorized, is CO3 2 minus. Now we're going to get rid of the plus and the minus sign, so it looks like this. Then we're going to crisscross the numbers. The 2 from the ion has to go around all of the CO3. This is where parentheses come in place. So we make it look like this. Now we ensure the subscripts that we did the crisscross on are in the lowest whole number ratio. And that's this 2 and that 2. Both are divisible by 2, FeCO3. When looking at the subscripts, we ignore the subscripts within the parentheses. So the 3 on the CO3 doesn't count for this. The total cationic charge, 1 iron times 2 plus. Total anionic charge, 1 CO3 at 2 minus. And we add those numbers up, you get 0. That's a valid formula. What is the ionic compound made from zinc and acetate? That is for you to do. Stop, figure it out, come back, and I'll walk you through it. Go. And you should have gotten one of these two formulae. Remember that what's in the parentheses are the same, just written slightly differently. So you write out the ions. Zinc is always 2 plus. Acetate is CH3COO1 minus. Step 2, get rid of the plus or the minus sign. So now it looks like this. Do our crisscross, bring the 2 down around the acetate, the 1 to the zinc. So it looks like this. We ensure that the subscripts outside the parentheses are in lowest whole number ratio. They are. The total cationic charge is 2 plus. The total anionic charge is 2 minus. So the overall charge is 0. And that's how you put together ions to make ionic compounds which are also called formula units. Now, a question you may be asked is, which has a stronger ionic bond, one compound or the other, in this case sodium chloride or potassium chloride, and then you'll be asked to explain your answer. This is where Coulomb's law comes into place. Now, to refresh your memory, Coulomb's law states that force is related to Q1 times Q2 divided by D, and for ionic compounds, Q1 is the cationic charge, Q2 is the anionic charge, and D is the distance between the nuclei. So you take a look at sodium chloride. Sodium has a Q1 of 1 plus, chloride is 1 minus. Potassium chloride. Sodium and potassium are in the same group, so they have the same Q1. Chloride is chloride, so it has the same Q2. So note the numerator has no difference between the two. So there must be something to do with the distance between the nuclei. Now, the sodium ion is smaller than the potassium ion because sodium has fewer energy levels, as demonstrated here with the sodium ion having 2 energy levels and the potassium ion having 3 energy levels. So D will be smaller for the sodium chloride than the potassium chloride. The smaller the D, the larger the magnitude of the force. Therefore, sodium chloride would have the stronger ionic bond. It has a stronger Coulombic force. How about sodium chloride and magnesium chloride? We look back at Coulomb's law. Sodium chloride, we already know, has a Q1 of 1 plus and a Q2 of 1 minus. Magnesium chloride, Q1 is 2 plus, Q2 is 1 minus. So the magnitude of the numerator is larger for the magnesium chloride than the sodium chloride. So that already increases the force or makes that a stronger bond. Now the magnesium ion is smaller than the sodium ion. Both are in the same period, but the magnesium ion has a higher effective nuclear charge than the sodium ion, so it pulls the outermost level in a little bit closer. So the D is smaller for magnesium chloride than sodium chloride. So in this case, you have a larger numerator and a smaller denominator. So the magnitude of the force for the magnesium chloride will be greater than sodium chloride. So magnesium chloride has the stronger ionic bond. So here's one for you. Which has the stronger ionic bond, magnesium oxide or magnesium chloride? Explain your answer, and remember, explain means give the reasons. Stop, figure it out, come back, we'll go through it. Go. And the correct answer is magnesium oxide. We take a look at magnesium oxide. We get Q1 equals 2, Q2 equals 2 minus. For magnesium chloride, Q1 is 2 plus, so that's the same, but Q1 is 1 minus. So the magnitude of the numerator is larger for magnesium oxide than magnesium chloride. Additionally, the oxygen ion, or the oxide ion, is smaller than the chloride ion. Once again, oxide has 1 fewer energy level than chloride. So the D will be smaller for the magnesium oxide than the magnesium chloride. That means magnesium oxide has a larger numerator and a smaller denominator than magnesium chloride. So the Coulombic forces are greater for magnesium oxide. It has a stronger ionic bond. So to review, opposites attract. So ionic compounds or formula units have anions and cations. The overall charge of the compound is 0, so the total ionic charge must equal the total cationic charge. Coulomb's law comes into play when you're asked to explain the strength of the ionic bond. We use the crisscross method to make the compound. In step 1, you write out the ions. In step 2, you get rid of the plus or the minus signs on the ions. Crisscross the numbers and move them into subscripts, using parentheses for polyatomics if need be. Ensure that the subscripts are in lowest whole number ratio. Do not touch the subscripts that are within parentheses. And if you think about it, in actuality, an ionic formula is an empirical formula. In the next lecture, we're going to show how you can figure out what the ions are when you separate them in an ionic compound, something called dissociation.